So today, Jacob Radford is going to be presenting a seminar on his master's degree work at North Carolina State University with Gary Lackman, but also talking about what he's working on with the DTC visitor program, applying mode to the work that he's been undertaking. So have at it. And there might be a few people trickle in. Don't be disturbed by that.
All right, thanks for the introduction. So today my talk is going to be on the verification of high-resolution banded snowfall forecasts. I apologize in advance, especially to Lindsay and anybody else that may have seen my NWP talk, because it's going to be very similar, but hopefully I have enough new stuff in here to keep you awake.
All right. It's always good to see things twice. It sinks in more.
I always love starting with this slide just because I love this picture. This is just like a couple miles from where I live in Raleigh. It happened a couple years before I was there, but it kind of shows the potential impacts of a bad snowstorm, even if there isn't a ton of precipitation. So snowbands can present extremely hazardous travel conditions due to their high precipitation rates, lowered visibility, and sometimes rapid onset. And in theory, high-resolution weather models like the high-resolution rapid refresh should be able to predict these bands, because the high-resolution rapid refresh has a resolution of 3 kilometers, and at minimum, the bands we're looking at have a width of about 20 kilometers. So my research questions first, objectively, how should we define a snowband? It's telling me to log into the internet now. So how should we define a snowband? We need some algorithmic way to identify snowbands in both forecast and observed radar imagery, so we can compare the two. Once we've done that, we can assess how well high-resolution weather models actually predict the occurrence of snowbands by comparing images like the one I have below here. So the data that I'm using is NexRad base reflectivity, or N0Q mosaics that are produced by the Iowa Environmental Mesonet. These have a 0.5 dBz or 0.5 kilometer and 0.5 kilometer resolution. I'm also using real-time mesoscale analysis, or RTMA temperature fields, which have a 2.5 kilometer resolution. And also for the model data, I'm using NCEP's high-resolution rapid refresh, or HRR, at every third initialization, which has a 3 kilometer resolution. Now, before I get started actually comparing the model and the observations, I needed to do some pre-processing on the data. So everything was interpolated to the HRR grid to start, which is the 3 kilometer grid, 1059 by 1799. And then I needed to do some masking as well, because in the observations we have areas where we have poor radar coverage, particularly in mountainous areas, whereas the HRR has pretty much universal coverage over the CONUS. So I masked out areas of potentially poor radar coverage from the HRR. And I also restricted the domain to areas east of the Rockies, or 104 degrees west, partially because we have different forcings in the Rockies compared to in the eastern U.S., but mostly just because this is a radar-based study, and the radar coverage in the Rockies is pretty abysmal. So we just decided to toss everything west of the Rockies out. There are a few different kinds of snowbands. These definitions are taken from Novak's paper in 2004. So a single band would be a band that's over 250 kilometers in length, between 20 and 100 kilometers in width, with a minimum intensity of 30 dBz and maintained for at least 2 hours. And then we also have multi-bands, which are more fine-scale bands, so you have at least 3 fine-scale bands with periodic spacing, similar orientation, and a much lower intensity threshold, maintained for at least 2 hours again. And then there's narrow cold frontal, which is over 300 kilometers in length, and is more looking at its position relative to a cyclone, so it's along a surface cold front. It has a minimum intensity of 40 dBz. And then there are transient bands, which are basically just all of the bands that meet all of the other criteria except for the 2-hour duration minimum. So in our study, we're mostly looking at single bands because they're pretty much the low-hanging fruit in terms of band predictability. We figure if the model isn't going to predict single bands well, then it's definitely not going to predict multi-bands well. So we figured we'd start there. Transient bands are also included in our study. We didn't have a duration minimum like Novak has of at least 2 hours. So pretty much as long as it occurred for at least one time frame, then we counted it. So what is a snowband objectively, at least in a way that we can implement into a coding algorithm? And we can start with Novak's definition that I showed on the previous slide, which is 20 to 100 kilometers in width, 250 kilometers in length, and a 30 dBz minimum intensity. And it seems like that should be pretty easy to implement objectively, but there are a few alterations that we had to make before we could actually implement it. Because there are a couple problems with this. So the biggest problem is that a 30 dBz threshold is significantly too high. So I actually ran my detection algorithm with a 30 dBz threshold for our the 4 winter seasons we have, which is 2014 till 2018. And when I did this, I only got 71 bands over 4 seasons. And even just, a cursory glance through some of the data will tell you that there are more than 71 bands over the 4 seasons. And I think the reason he chose such a high threshold is that he was mainly focused on pretty intense storms in the Northeast, whereas we're focused on a much larger domain. So we need to adapt that threshold for our study. And then the other problem with Novak's criteria is that he had a 20 to 100 kilometer width criteria, which is fine for subjective ID. I mean, that's about what you would typically identify for a band. But because we're doing this, with a program, a computer program that's not necessarily good at shape identification, we have to fit these regions with bounding rectangles. Well, we could fit with different objects, but we chose to fit with bounding rectangles. And because we do that, it's relatively hard to get an accurate width. A bounding rectangle tends to overestimate the width of an object. So using 20 to 100 kilometer range can be too narrow or limiting. So I just mentioned the problems with using a 30 dBz threshold, but I think in general we probably shouldn't use a set reflectivity threshold like 20, 25, or 30 dBz. And that's because, so I have an example here. So we have a band in this pretty intense precipitation region in the Northeast. And if we choose a set reflectivity threshold that's too low, we essentially mask out the entire band. So this is a 20 dBz threshold, but it's much too low, and we've identified a really large precipitation region instead of just trying to get at that small band. Can you see my cursor? Yeah, the small band embedded within the precipitation region. So using a too low of a set reflectivity threshold tends to mask out the finer scale features. So as an alternative, we developed this heterogeneity method, which is basically redefining bands as a narrow region of reflectivity that's significantly more intense than its surroundings. And this has the benefit of tailoring the threshold to unique event characteristics. So the band criteria for an event over Massachusetts, for example, may be different from an event over Wisconsin. And this essentially targets the problem that I showed in the previous slides by not masking out higher intensity bands with low thresholds, because if you have a large region of intense precipitation, your calculated threshold is going to be higher and you're going to get at your fine scale features better. So you can see applying a heterogeneity thresholding method to this case, we have a better fit to what we would actually classify as the band in this case. So what is the alternative now to using a set size criteria? So instead of using that 20 to 100 kilometer width minimum, or width criteria, what can we use instead? So we decided to use an aspect ratio method, which has some precedent in literature. And basically, it just says that bands need to be significantly longer than they are wide. So we used an aspect ratio, or a width divided by the length of less than or equal to 0.33. So basically, it's 3 times as long as it is wide. And this means that longer bands are allowed to have a greater width, which I think makes sense intuitively. And it gives more size leniency to compensate for sometimes poor fits of bounding rectangles. And one final consideration that I've kind of been getting at in the previous slides, which is that bands are typically linear, but they sometimes exhibit significant curvature. So this band over the Northeast, this is from March of 2017. We have a band here, but it's significantly curved. So when we fit a bounding rectangle to it, it's a pretty bad fit. We'd probably only measure the width with a human eye from about here to maybe like right here, but this bounding rectangle is significantly overestimating the width. So even using the aspect ratio method, we probably aren't going to catch this band. So as an alternative to catch these sometimes curved bands, we decided to look at the solidity of the object, which is the contour area compared to the area of the convex hull of that contour. So the idea is that the area of the contour itself is going to be relatively low compared to the area of its convex hull. And finally, we need some way to determine precipitation type, because we're focused on snow bands, not all bands. So we considered a couple different things. We considered her analysis categorical p-type, supplementing the observations, basically. But instead, we chose to just go with a 0 degrees Celsius temperature mask using RTMA data, mostly just for simplicity's sake. Of course, this isn't perfect. It assumes that all freezing precipitation is going to be snow, whereas it could be sleet or freezing rain. But for our purposes, it works fairly well. So the band identification process looks something like this. First, we convolve the reflectivity data to bridge over any small discontinuities and make sure any bands aren't going to be broken up. And then we thresholded and binarized using some distinguishing values. So we can use set reflectivity thresholds like 20, 25, or 30 dBz, or we can use our heterogeneity method, so using 1, 1.25, or 1.5 standard deviations above the background reflectivity. Once we've done that, we fit minimum area bounding rectangles to the remaining regions. And if the length and width of that rectangle meet whatever band criteria we chose, so we can use Novak's definition, which was 20 to 100 kilometers in width, or our aspect ratio method of less than 0.33, and the temperature is less than 0 degrees C, then we would positively ID it as a snow band. So I did a subjective manual classification of observed reflectivity images from 2016 to 2017. Basically just went through it's hourly intervals, so I went through every hour and classified whether there was a band or not as sort of a training set. And then I tried to identify the objective definition of a band that most closely matched my subjective classification. So what choice of reflectivity threshold and what choice of band size criteria. I'm just going to tell you guys the answer now because I'm about to show it visually, but it'll probably be easier to follow along visually if you know exactly what I'm doing. But the best band definition we found was 1.25 standard deviations above the local background snow reflectivity, where we define the local background as the mean reflectivity of each contiguous precipitation region above 0 dBz. And then the best size criteria was a 250 kilometer length minimum and a 3-to-1 axis ratio, or a 1-to-3 aspect ratio, however you want to say it. And then we also have an alternative size criteria to catch those curved bands. So still a length minimum of 250 kilometers, but instead of having the aspect ratio criteria, we require a solidity of less than or equal to 0.5. So this is what the process looks like visually. We start with a base reflectivity image. This is November 11th, 2014. We have a nice band set up from southeast Nebraska to southeast Minnesota. And the first thing we do is we threshold at 0 dBz. So all we're left with are contiguous precipitation regions exceeding 0 dBz. And then for each of those identified precipitation regions, we calculate a threshold at 1.25 standard deviations above the background reflectivity. So we basically look at the distributions of the reflectivity in each of those regions. So the threshold is going to be unique to each precipitation feature. So the feature here in the central U.S. is going to be something like 23 dBz, whereas the threshold over here in Maine is going to be lower, around 18 dBz. And once we threshold at those new values, we're left with only precipitation features that are 1.25 standard deviations above the local background reflectivity. And then for each of those remaining regions, we fit a bounding rectangle. And then we apply a 32 degrees Fahrenheit temperature mask. And if at least 50% of the contour falls in the below 32 degrees Fahrenheit area, and the bounding box meets our size requirement of 250 kilometer minimum length and 3-to-1 aspect ratio, then we positively ID it as a snow band. And we can see that we have successfully identified the snow band in the central U.S. So like I mentioned before, the best definition was 1.25 standard deviations above the background, 250 kilometer length minimum, and a 1-to-3 aspect ratio. And this has a few benefits. So I think when we look for a band, we tend to look for some region of heterogeneity rather than for a particular reflectivity value. And like I mentioned before, fitting a bounded rectangle to a region tends to overestimate the width. So I think the size criteria of an aspect ratio makes more sense than using a range. And the third benefit is that when we compare forecast and observed radar imagery, we're kind of comparing apples to oranges because we're comparing simulated reflectivity at a 1,000-meter level compared to base reflectivity. So using a standard deviation method kind of tailors the thresholds to each of those and tends to reduce error due to reflectivity biases in the model. So I have a few more case examples just to show that it's working as it should. So this is that same case I was showing, just more time frames of November 11th of 2014 with a band over the central U.S. So it pretty much identifies everything that we might consider a band. I think it does pretty well in this case. If we go on to the next case, this is a case that occurred on January 27th of 2015, a really nice large band over the northeast. And then this third case, this is kind of a special case. This is what's come to be known as the Pi Day storm. It happened March 14th of 2017 over the northeast. And this one's special because it has a lot of band curvature. So this is one that wouldn't be caught unless we have that alternative threshold, or that alternative size criteria of a solidity of less than 0.5. So there are some time frames in this one that you might subjectively identify as a band. Let me see if I can get it to one. It doesn't show my cursor. But like up here, you might identify that as a band. But I think overall it's performing pretty well and doing pretty much what it's supposed to be doing. So we applied this to the observations first to create sort of a snowband climatology. So this is for the 2014, 15, 15, 16, 16, 17, and 17, 18 winter seasons. We defined a winter season as November 1st through March 31st. And we see a pretty well-defined banding maximum from Nebraska east through Michigan, where they receive at least 30 banded hours over the course of the 4 seasons. And then there's sort of a secondary maximum over the northeast. And then we can do the same thing for the forecast. So I have 5 different forecast lead times, 3, 6, 9, 12, and 15 hours. You'll notice that the observed banding is a bit different from the previous slide I showed. That's because we cut out the 2014 to 2015 winter season because we don't have that HER data. And we also only looked at every 3rd hour in the observations because we only have every 3rd initialization of the HER. But it looks like the HER is getting the spatial distribution of banding just about right. It has the same spatial maximum in the Midwest from Nebraska through Michigan. So at least spatially, it looks like the HER is performing pretty well. And then these are some of the statistics I calculated for bands in the forecast compared to the observations. So except for the frequency, these are all just means, so basically the mean band. So the frequency of banding was about right. Between 400 and 450 bands were forecast compared to 419 observed. Length and width were about right, slightly overestimated in the HER forecasts. But I want to draw your attention to 2 fields that were quite a bit different in the HER forecast versus the observations. So the HER average forecast area was around 18,000 square kilometers. Whereas the average observed band was only about 13,000 square kilometers. Also quite different was the intensity of forecasted bands compared to observed bands. So the average forecasted band had an intensity of about 22 dBz, whereas the average observed band had an intensity of about 25 dBz. Now, of course, we're still comparing apples to oranges a little bit, comparing 1,000-meter reflectivity to base reflectivity. So on my to-do list is to compare observed and simulated reflectivity distributions and just see if the intensity differences are real or if they're just an artifact of post-processing or looking at 1,000-meter reflectivity compared to base reflectivity. And just anecdotally looking at the images, it seems like HER objects seem much larger and more diffuse than observed objects. So it looks like the climatology of HER forecasted bands is pretty good. It gets at least the spatial distribution frequency of banding about right. But what is the predictability of bands on a case-by-case basis when we match corresponding forecasted and observation times? And the initial answer was the predictability was very bad. So we matched up times from the forecast and observations and just identified whether the model got a hit or a miss, so basically contingency table statistics. So this is a performance diagram. On the x-axis, we have the success ratio, which is 1 minus the false alarm ratio. On the y-axis, we have the probability of detection, which is the probability that a band is forecast if a band is observed. And our success ratio and our probability of detection are around 35%, which is pretty abysmal. And that corresponds to a CSI of about between 0.2 and 0.25. So we have a seeming contradiction here, which is why is the climatology of her forecasted bands pretty good, but the predictability of bands on a case-by-case basis is so bad? And to help answer this question, I did some fuzzy verification, basically answering the question of what if we don't care that the her forecasted band at the precise time that one is observed, but instead just care that it gets close in time. So I did sort of upscaling. So I grouped forecasts and observations into coarser time windows. So, for example, if we have a band anywhere in the forecast from 2Z to 4Z, then that basically makes a positive identification for that window, and we do the same thing for the observations. And then we compare those time windows instead of individual time frames. And whereas originally we would have produced a false alarm because a band is forecast at 2Z and not observed at 2Z, and a miss because we didn't forecast a band at 3Z, but one was observed at 3Z, we now get a hit because both of those time windows have a band. And when we apply this to our data, we get significantly better results. So our success ratio and our probability of detection have risen from about 35% to around 50%. Our CSI is about 0.35. And this is just using a 1 hour time window. So that would basically be like in this case with a 2Z to 4Z time window. If we continue to increase the size of that window, so now a 2 hour window, we continue to see improved results, around a 60% probability of detection and success ratio. Our CSI is over 0.4 now. And then finally, if we have a 3 hour window, which is getting more at the question of if there will be a band rather than when and where exactly a band will occur, because a 3 hour window means that a band could be forecast at 0Z and observed at 6Z, for example, and still be considered a hit. But if we do use a 3 hour window, our success ratio and probability of detection are almost 65%, and our CSI is about 0.45. But there's a caveat with this, which is that we didn't implement any spatial constraints. So basically, if a band is forecasted over Maine and observed in Minnesota, if they occur at the same time, then we still considered it a hit. But how do we know if a forecasted band is the same object as an observed band? And that's where we're going to start using the method for object-based diagnostic evaluation, or MODE, which offers powerful capabilities to help us answer this question using fuzzy logic, matching, and merging. So we basically define some parameters into an interest function based on object properties. So, for example, the object displacement between the forecast and the observation, differences in orientation or area, intensity, complexity, soon, hopefully, aspect ratio. And it's kind of up to us how we weight these different parameters. So what we want to do is we want to get some forecaster input about what forecasters actually care about in terms of snow bands. But this will allow us to create sort of a sliding scale from a poor to excellent forecast. So when we get the output of this interest function, instead of just being a hit or a miss, we're going to get something from 0 to 1 telling us if the likelihood that a forecasted and observed band are the same band. And ultimately, we're going to use this to tell us the worst and best forecasted band cases, and then hopefully look for patterns in these different cases to see what types of situations the HER excels at or underperforms in. So MODE is currently unable to do a nested or domain-varying threshold like my current algorithm does, so it can't threshold at 0 dBz and then calculate a new threshold based on each individual object's properties. But Randy Bullock and the DTC are currently working on implementing a MODE Python interface. So basically, users can define their own objects however they want, and then these objects can be fed into MODE via NumPy arrays. So it's basically going to combine the versatility of being able to identify your own objects in Python with the power of MODE's logic engine. So I've come up with sort of a revised procedure that we're going to be using mode. It starts off pretty much the same. So on the left we have the forecasted imagery, and on the right we have the observation. In the observation at least, there's a clear band in the Midwest. So first we threshold at 0 dBz, so contiguous precipitation features over 0 dBz. And then we calculate our new threshold at 1.25 standard deviations above the mean reflectivity. So then we're left with objects that are 1.25 standard deviations above the background reflectivity. And we still apply our 32 degrees Fahrenheit temperature mask if at least 50% of each of the object falls in the above 32 degree region. We essentially just toss it out. But then instead of fitting bounding boxes to those features, we're going to input those features into mode. So I've done that for this case, and I defined an interest function based on the centroid distance, the angle difference, the forecast the area difference, as well as the boundary difference. And it calculates an interest score for you, which is down there in the bottom right. So for this case, the interest was 0.9523, which is a pretty good score. So it means that in all likelihood, these are the same object in the forecast and the observation. So I took 135 cases, which I had previously identified as hits. So these were cases where a band was forecast and observed at the same time at just a 3-hour lead. And I ran mode for all of these cases using that equal weighting that I just mentioned. And we get a fair amount of cases that definitely are not the same case that get an interest score of essentially 0. But about 75% of the cases get an interest score of above 0.7. So for the most part, it looks like that when the work that we did previously, considering a band in the forecast and observation to be a hit if they occur at the same time isn't too bad of an assumption. They're typically the same object. So in conclusion, the best objective band definition we could come up with was 1.25 standard deviations above the local background reflectivity. We had a minimum 250 kilometer length and a 3-to-1 axis ratio. The HER and observed band climatologies are very similar in frequency and location, about 400 forecasted and observed bands when we only look at every third hour. They had the same maximum corridor extending from Nebraska to Michigan, but HER bands did seem to be larger in area and have lower intensity, which again is worthy of further investigation. Then when we matched forecast and observed image times, it initially indicated very poor predictability. Our probability of detection was only 35%. Our false alarm ratio was 65%. If we allow for up to 3-hour timing discrepancies, it drastically improves performance, so our POD was over 60% and our false alarm ratio was below 40%. And in summary, HER snowband forecasts are definitely still far from perfect, but they're much better than the traditional verification might imply when we just match corresponding times. So our next steps, I've kind of gone over these already, but we're going to be using mode to do an object-oriented verification, matching and merging of precipitation features based on object properties. So essentially creating a snowband verification metric based on object properties like distance, orientation, size, or intensity. And then ultimately, we hope to investigate any discovered model deficiencies, so assess the impact of the calculation of simulated reflectivity, and assess the types of cases that the HER performs exceptionally well or poorly in. I'd like to acknowledge our NOAA C-Star Award, NCAR, particularly Randy Bullock, John Gotway, Tara Jensen, Louisa Nance, and Jamie Wolf for hosting me these past 2 weeks. Our collaborators, my advisor, Gary Lackman, the Iowa Environmental Mesonet for our reflectivity data, and NCSU for the RTMA data. And I'll take any questions anybody has. Yeah.
Maybe I missed it, but on the probability of detection, you did the Minnesota to Maine, at least not California to Connecticut, but what was it really that broad, or was it a tighter tighter constraint? I realize using mode now will help you chase.
Yeah, so we had when we did the probability of detection, we had no distance restraint at all.
Okay.
Yeah.
So that gives you sort of a beginning baseline.
Right. So in all likelihood, our skill scores are only going to go down from that.
Well, you'll get more information.
Yeah.
Okay.
So I had a question along the same lines. So you're dealing with shorter range forecasts, then, correct?
Yeah.
So by not having that spatial limitation, if you went to longer range forecasts, do you think there would be more disparity potentially between?
Yeah, for sure.
Yeah.
I think if we did. Yeah, and that'll be interesting. Once the HER-E and we're going to hopefully extend this into ensemble forecasting too.
Oh, okay.
So, once we start getting higher resolution models at longer ranges, I think yes, we will see more discrepancy in terms of location.
Uh-huh. Any other questions for Jacob?
Yeah.
John.
When you listed the object intensity threshold, those were like the object definition threshold? Is that right? When you said that, like in her, it was 25 dBz or something.
Oh, let's see.
Yes,
Yeah,
right.
yeah.
25 versus 22
Yeah.
or 21. Is that the object definition?
No, that is not the threshold. That's the average intent. So the mean reflectivity inside the object. So there could be embedded, more intense features embedded within the band that are, make it a higher value.
But ultimately, the threshold, for
Right.
the object definition threshold, is really determined by what's going on in the surrounding area, right?
Mhm.
So I guess I wonder how the difference in the full distribution of values in the obs and forecasts kind of impact that choice.
Yeah, and that's something, I need to look at, is just looking more into the distribution of reflectivity in the observation compared to the model simulated reflectivity.
I think it's really, really interesting what you've done, like using kind of object tailoring the threshold object by object. I think is a really cool idea. So we should talk about how we should incorporate that as a feature within mode itself.
Yeah, sure.
Can you remind me what the resolution of the observation data set is versus like the model?
Yeah, so the observed, let's see. So the reflectivity mosaics have a resolution of about 0.5 kilometers, and the HER has 3 kilometer resolution. So,
Okay.
yeah.
So I guess from that standpoint, would that describe some of the reason why you would end up with larger objects in the HER?
It's possible. We interpolated down to the HER. So in theory, there shouldn't be difference due to the resolution. But I think there have been some studies that even interpolating, you retain some of the information you have from a higher resolution. So.
Right. Well, and I think it's important to keep in mind that when you're dealing with model data, it doesn't really resolve behavior all the way down to the resolution of the model itself.
Right.
So you'll end up with a little more spreading just naturally that way. So if it went the other way, that the objects are smaller, and I might have been like, whoa.
Yeah.
Anyway,
Any other questions for Jacob?
seems like it would be cool to apply it to mode time domain as well. But I was watching the animations, though. I saw sometimes the feature would flicker off and on based on falling below and then above. So that might prove problematic for mode time domain.
Right.
Keeping a continuous feature through time.
Yeah.
Oh, I have another question. When you did that time variation, did you have anything to make sure you were only counting an object once, or?
Yes.
Okay.
I did.
No double counting,
No.
right? Okay. I was curious about that. Anything else?